the concept of robotic will address two main goals. First of all, correspond to labor shortage. If we have to build a community and we don't have enough labor power, we can have the robot come in, whether fully automated or semi-automated, which is something related to human-robot collaboration. We can tweak it as needed. The other thing that actually one of our larger goal, which is trying to create a new movement in construction where the Made in America is one of the leading goal for our robotic station. We need things to be made here.
Thank you, Dr. Alwisy. So you're Aladdin Alwisy. You're a Ph.D. and an assistant professor at the Rinker School of Construction Management and the director of the Smart Industrialized Design and Construction Lab at the University of Florida. You're also leading in the DCP side the Industrialized Construction Engineering program. And just to talk about a little bit of your research interest, you're interested in developing and assessing practices for the future of industrialized construction and tackling specific technologies like robotics, sensing technologies, machine learning, augmented and virtual and mixed reality, simulation, lean manufacturing, all of this to reduce the expense of design, manufacturing process, and systems control in general. So yeah, we can talk about maybe in a general sense, industrialized construction. Because at the beginning, when I saw your profile, it was more robotics for construction. I didn't really know the term industrialized construction was a specific thing. So maybe you can talk about that. Like, what is it, and how do you become interested in that?
So that's a very good question. Industrialized construction is not new. Industrialized construction goes back to the 40s and 50s.
Okay.
So the moment that you don't build on site, the moment you don't follow traditional construction processes, that is industrialized construction. In the early 40s, 50s, they used it to support camps, to support military operation, where they needed to have permanent shelter quickly. So what they used to do, build modular construction units, install them on site, and help the, I would call it, living conditions of people working in rural places. Now, when it comes today, industrialized construction is much broader. So industrialized construction, it encounter off-site construction, modular construction, banalized construction, and even manufactured construction. So think about it as the umbrella for prefabrication. Now, we're trying to avoid the word off-site because in the past, we used to go and build everything in a factory. As you can see here, we do have a manufacturing line, whether it's human-centric, whether there is equipment, whether it's robotic, but it is done off-site. The prefabricated or manufactured unit gets transported to the site and assembled there. The reason I'm saying we're trying to avoid that because of multiple reasons. First is 3D printing. 3D printing falls under prefabrication, and part of industrialized construction engineering program, we acquired one of the largest 3D printer in the US, and very soon we're gonna have a few demo projects to show how we can integrate 3D printing within the construction process. So this moves us from off-site to on-site. On top of that, the technology you see here, we're hoping in the near future to have it mobile. We're gonna have factories that get established next to the construction site, and within days, we can finish what usually take months or even years. So again, if I want to summarize it, industrialized construction is innovative construction process that changed the way we build. It focused more on prefab, on creating the construction system needed separately from the site itself, having it assembled within a fraction of the time, and there is a very high potential of cost reduction as well.
Right. I imagine the latter piece that you mentioned is the specific optimization goal, right? Is the goal overall, maybe that's a question, right? Is the goal overall always to reduce cost? I imagine like also time. So that's why you have all of these different techniques, right? You mentioned offsite and onsite because before, what I was thinking is that you would bring everything to the site and construct everything in there, but then you have this new paradigm of building stuff in some factory, bringing it to the actual place of construction that is already sort of assembled, so it reduces cost. So like what are the metrics like that you're trying to optimizing here, and how does, for example, you mentioned like modular construction and panelized construction come into play in this?
That's a very good question. Again, when we talk about time and cost, because this is literally the first thing any project manager thinks of, how to make it faster, how to make it cheaper, but this is not by any means the limit of the performance metric we focus on. I can give you a very quick example, which is waste reduction. When we're automating processes, whether using robotic system, whether even automating the design process, we try to optimize the sequence of assembly. We try to optimize the cut list of different materials. So material waste is one of the things that we absolutely try to reduce, and this has impact on cost and on the environment. The other thing, which is energy performance, when you build things in a factory, and when I say in a factory, it doesn't mean off-site. As I mentioned, very soon, we plan to have factories established next to the building temporarily throughout the construction process and support the construction need of this building. So whether this factory off-site or on-site, whether the 3D printing penalized or modular, we could improve the energy performance by enabling manufacturing techniques and assembly techniques that would have been semi-impossible, if not extremely expensive, with the existing manual processes. So we talk about waste, we talk about energy, another aspect which is quality. Once we develop the processes, refine them, tweak them, now man-made error will be reduced. We're all human. If I work on something, sometimes I do it left, sometimes I do it right. When we're integrating computer vision, when integrating AI, when integrating robotics, automation, digital twin, all of those buzzwords, I don't like to mention it back to back, but all of these are tools that we use toward a common goal. The common goal could be, as we mentioned, energy performance optimization, material waste reduction, CO2 print reduction, material, I would call it processing reduction, because we're even implementing something called lean manufacturing. And in lean manufacturing, the word waste is not only for material. So waiting time in a factory or in construction process is waste. Overprocessing is waste. So there is a lot of things that we can focus on. The other thing is resilience, because when we're talking about robotics, AI, or digital twin, we're creating a resilient construction process that is not affected by any disruption to labor. It's not affected by disruption to material, because we do have an established process. And if we have factory and we plan ahead, we know exactly what kind of material we need. So it's resilient construction process. It creates resilient community as well. So let's assume, God forbid, there is a new hurricane coming and we have a community got hit. We can have our station, whether here or on site, be deployed within a day or two, and we can build a community that should usually takes maybe months or year within a few days. So resiliency, sustainability, material cost, of course, waste, time. And again, I'm trying to think about if I missed some quality. So it's almost everything. The whole idea is once we have systematic procedure, we can define a goal, whatever this goal is, and we try to achieve that goal by improving, refining, and I would call it optimizing our processes.
Right, right. So you've talked about kind of the challenges that come in normal construction, right? Like that it's labor intensive, that it takes time, maybe it's a little bit more expensive, and you're trying to use these new technologies to improve all of that. So what are the, maybe in general strokes, and then we'll go a little bit more in technical detail, is what are the visions, what are the benefits that you're trying to bring by using all of the technologies that and of course you can mention maybe individual ones if you want. So like robotics, computer vision, AR, VR, MR, what are they all bringing to the table to improve all of this?
So again, when it comes to construction challenges, we're lucky enough that we have too many. Sarcastic. So we have a lot of challenges that we're trying to address. Labor shortage is one of them.
Right.
And
right.
the concept of robotic will address two main goals. First of all, correspond to labor shortage. If we have to build a community and we don't have enough labor power, we can have the robot come in, whether fully automated or semi-automated, which is something related to human-robot collaboration. We can tweak it as needed. The other thing that actually one of our larger goal, which is trying to create a new movement in construction where the Made in America is one of the leading goals for our robotic station. We need things to be made here. If I need to develop a complex wall systems, I can have this done here in Gainesville. We don't need to go buy it from a different resource just because labor cost there is cheaper, just because they may have more labor hours. So we're trying to move toward the Made in America. This is one of the main goals for robotic. We're trying to address the labor shortage. We're trying to address affordability issues, because when I mention cost and time is more related to resilience, more related to disaster recovery, but cost is still a major issue. Now, our current system is only doing panels as in framing, but we're hoping in the next 3 to 5 years to build the whole building, including MEPs, mechanical, electrical, plumbing, including interior and exterior finishes. So what that will do, reduce the labor cost, which is a big portion of the construction cost. When you reduce the labor cost, this should be translated to lower price for entry. If people with lower income need to buy a house, instead of them spending anywhere between $200,000 to $500,000, and this is for an average house, now they can go for much lower than that. So supporting affordability is another aspect. And if I want to summarize it again, the three main goal is first, Made in America and addressing the labor shortage. Second, affordability, of course. And third is disaster recovery. And this is not in order. Any of those three goals are great, but these are the three key areas we're trying to address in moving toward robotic. And when it comes to digital twin, AI, all of these are tools that support our automation. And in this lab, it's the core, or robotic is the core of our research efforts.
So what I was thinking is why trying to make it in America? You mentioned that maybe sometimes it's cheaper to do it, bring resources elsewhere. Is it because you're maybe sort of like the same reasons like the administration wants to bring manufacturing to the U.S. is like just to reduce the dependency on external parties? Like, would that be one of the reasons, or what other reasons do you envision?
Absolutely. I don't know if you know, but recently, of course, you're aware where prices of even raw material became much higher.
Yeah.
Now, this is for us is a big disruption, especially if you work on a project. Let's assume a project manager priced a project for X million, and they sign the contract. It's a lump sum, meaning the general contractor has to build this project within this budget.
For X million.
Now, you do have disruption in material, disruption in labor. How we're going to address that? Now, what happened these days is either the general contractor take the hit, if it's not significant, and basically they're losing money, they're losing their profit, or when the change is significant, they start negotiating with the owner, whether it's private or public. It's not more money, it's more or less, give me my money back. So basically I said, it's going to cost me, let's say 10 million, based on a cost of 9.5 and a profit of $500,000. But now my cost ended up being 10.5 million.
Right.
So the builder actually losing money if they build it for 10 million. So again, these disruptions are very common in construction. Now again, based on the economy, based on the cost of the material, labor availability, the impact could be larger or smaller. But when we move to Made in America, we're controlling not only the labor, but the material as well. As I mentioned, we can have our storage include all the raw material, the wood stud, the OSB sheathing, gypsum board, pipes, wiring, that needed for the next year or so. And then I can build as needed. We're following something called lean manufacturing, which is a pull system. We may have storage of material. And I know in lean, if someone familiar with lean might say, but storage is a waste, and I'm aware of that. But this is the balance between storing material versus storing finished product. So we store material to avoid any disruption in material supply, but we never store finished product. Finished product has to be a pull system. Pull system mean I know what need to be done this month. I'm gonna make sure to finish the work that's needed for only this month. Just in time policies, just in time scheduling. And this will enable us to utilize larger portion of our factory for manufacturing rather than storage of completed product. So to go back to Build in America, all of these uncertainty, if we get the Build in America back, get the economy back here, we don't have to worry about that. Another thing, which is job creation. I know it sounds contradicting when we say reduce labor costs but create job. But the answer is go back 50 years, 100 years ago, where they moved from horses and car to cars. I actually had this discussion with one of our admin in the university, and I'm like, we're not trying to reduce jobs, we're trying to replace, upgrade jobs. And he's like, I agree.
And create new industries too, right? Like, as you said before, my automotive industry did not exist, and now it's gigantic. Right?
And there are so many new jobs that people never thought of. When we have the station, yes, you may not have to have a worker who's carrying OSB sheeting that weighs 50 pounds 100 times a day. By the time they go home, their back hurts. By the time they're 40, they have a million health issue. Now we have the robot doing all of those heavy lifting, all of these, I would call it physically demanding, dangerous tasks, and leaving creative tasks for a human worker. Human worker, instead of learning only how to cut a piece of wood, now they're going to learn how to run a robot. And I don't mean coding, because that's the other thing that people in construction are afraid. I'm not going to learn how to code a robot.
Right.
And I'm like, you know how to use Windows. You know how to use your phone. Have you ever, some of us might, but construction people, have you ever had to go and develop an app? Have you ever had to go and program your Windows to make it work? So this is what we're trying to do. We're trying to move from manual job to more advanced job with advanced technology. Another thing that a new, I would call it Gen X, Gen XY, every time there is a different one, new generation who are looking at construction as outdated, as dirty, as manually job. Now they can understand you can work in construction and do similar work as if you're working for Google or Microsoft. You will be managing the job behind your desktop, coming doing site visit just when needed. So encouraging new careers in construction, opening new doors is the job creation. And when we say made in America, this is permanent jobs. Construction is very seasonal. If people have a 12-month job in construction, these are the lucky one. They work 6 months, 8 months, 12. Now again, larger company might have their own permanent crews, but the majority of construction company, the smaller one, they'll be lucky to work 8 to 9 months a year. Now, this instability, uncertainty affect morale, affect financials, affect so many different social issues. If someone knows, I'm gonna come to this factory, I'm gonna come to this site, and I have a job 12 months a year, I know what I'm doing, it's not physically demanding, I'm working almost in IT while actually building things in real life. So all of those changes are part of the Build in America. Disruption, job creation, promoting construction as a new career for a new generation or next generation, and of course, trying to improve the overall process.
How does robots are different to manufacturing? Because I think when I think of successes of robotics, I only think of a few small industries, like that's something like robotics really was game changer. The first one that comes to mind is manufacturing, right? Like an Amazon, for example, right? Like, or not even an Amazon, because Amazon is like distribution, right? Like that's maybe like a newer thing, but I don't know, like some automotive factory that, as you said before, there was like a single person like drilling these holes and drilling the same hole for hours and hours and hours. Now you just have a robot, right? Like that the only job is to do that repetitive task almost like 24/7. So that has been like a very big success. Sometimes jokingly, I say like the only other success that I think of is like vacuum cleaner robots.
Sure.
But and we're coming there, right? Like we're getting there. But how is that construction different to manufacturing?
So this is one of the fundamental challenges we're trying to address. For 3 years since I joined Rinker, I tried to educate people about the difference between manufacturing and construction. It was difficult for people from both sides to understand what we're doing because people in manufacturing, they assume we have robots. I really can't remember the exact date, but I had searched it on Wikipedia like since the 30s, over 100 years. So robotic arm has been there for this long and they're doing great.
Right.
So people in
Success,
manufacturing, they assume we can adopt the exact same processes, the exact same technology to construction. So it's nothing more than building a new case for construction. Not really, and I'll explain why. On the other hand, people in construction, they look at it as this is not what we do. They see the challenges, they don't see the solution. So people in manufacturing, they see the solution as it's a robot, it can do it. Solution is there. In construction, it's the exact opposite. We know how hard it is to do it. It's impossible to be done in robot. Now, what people in construction see are the key challenges in construction. They know that construction is unique. Each project is different. Even if I have the exact same design, same layout, when I move from site A to site B, I may be working with different crews. Remember, it's cyclical. We don't have 12 months. People might go to another job. We may have different weather conditions. We may have, due to material shortage, different material. I used frame A, and now I have to use frame B. So there is a lot of changing, and these changes makes it impossible for a machine like robotic arm, especially industrial one, that's built and designed for repetitive task. Repetitive task mean they're amazing when you tell them do the exact same thing a million times.
Right. Like
Very
the
precise.
drilling that I was mentioning, right? Like just that robot that drills
They'll do it
infinitely many times. Right?
perfectly. They'll do it much faster than anyone else. But come tell it, we have 10 houses. Each house has completely different floor plan, completely different designs. Each house could have different material, different, I would call it assembly processes, and you may have to work even with different crews. Figure it out. Again, construction people see the challenge, they don't see the solution. Manufacturing, I had people from mechanical engineering actually coming, and they're like, we can't do that. I'm like, really? Try to do it. Please, I challenge you to do it. Because the only, I would call it successful example that integrated robotic construction are few of the larger company where they had to spend over $10 million on a simple assembly line. Again, the $10 million is my estimate. I didn't go and check, but when I'm looking at their factory, there is maybe like 10, 20 robotic arm with a very intensive manufacturing strategy because they try to address each and every variation in a single robotic station. This doesn't work for us because they did overprocessing. They had very complex system, extremely high capital cost. And all of this actually negatively affected the integration of robotic because the early adopter of robotic, they did not have enough expertise to merge between manufacturing and construction. They tried to adopt the manufacturing concept on construction. But to do that, they went and created different station for almost every variation possible. This doesn't work in construction because if you do that, first of all, this robot has a lifespan. I know it's long, it's like 100,000 hours or so, I can't remember exactly, but eventually you have to replace them. The end effector has to be replaced. Now, if the reduction in the material cost is not justified by the increase of capital cost, then technically I'm literally spending more money to build the same component. Another thing that people in manufacturing don't understand, in manufacturing you do have quality control, but their quality control is yes or no. I have a good product, I scan it, it's good to go. The product is not good, discard it and keep going. Doesn't work in construction. Now, you may have seen the video we have in our station. Almost 3 years ago, we had the first prototype. We have 3 more to come. We're up and ready. I can literally deploy it in a factory and it will manufacture a wall panel. I haven't deployed our station in a factory yet for one reason and one reason only. The only way for our station 3 years ago to be deployable in a factory is for us to use something called mechanically graded lumber. Mechanically graded lumber is different from traditional lumber, visually graded or
This is
regular
wood,
one.
right.
Exactly. Mechanically graded lumber, the piece of wood is dimensionally correct. When we say 2 by 4 by 8, as in 2 inch, 4 inch by 8, 1 inch and a half, 3 inch and a half by 8 feet, it's actually this dimension. If you look here, and if you've ever went to Home Depot or Lowe's, go grab a piece of stud there. You're gonna see that half of them, if not more, twisted, bent, they might have nuts, they might be chipped. Now, how will the robot correspond to that? If we follow the manufacturing procedures, we scan the piece of wood. If it's not working, I'll throw it away. I will almost never use any of those pieces of wood.
You throw away half of them, yeah, as you said. Yeah.
And if I buy mechanically graded lumber, I'm doubling the material cost. So the piece of wood that costs $2.5, $3.5, it will be $5, $6, possibly $7. So the cost reduction does not exist. This is number one. Number two, when it comes to manufacturing, especially in construction, we want to reduce the labor cost without affecting the material cost. And this is why we had to wait. I have 2 of my PhD students working on developing software solution. We actually have a paper under review that utilizes computer vision to detect the shape of the piece of wood, and we're going to try to adjust our manufacturing strategy online to account for any deviation. So let's assume you have your target or TCB at X1, Y1, Z1, Zeta X1, Zeta 1, Zeta Z1.
Right, the position that you want to put your...
The 6 DOF or
Right,
degrees of freedom.
right.
Now, in the next year or so, we're hoping once we apply our algorithm, we're going to first scan it, know the exact geometry, and after that, we're going to go adjust the final target that the robot has to utilize to assemble the wall frame using this DOF geometry. Now, again, it's easier said than done. And the reason I'm saying that, another thing that we heard from manufacturing, but computer vision has been there. It's easy. I'm like, not really. It's perfect for manufacturing. I'm not saying they couldn't have done it for construction. They could. But people who designed cameras, industrial camera, people who thought about LiDAR, they did not have construction in the back of their mind. People who designed LiDAR, they were more thinking about drones. They're thinking about cars. They're not thinking about a guy who's trying to scan a piece of wood. Same thing, people who designed industrial camera. They're thinking about this manufacturing environment where you may be 1 foot, 2 feet away from the component with perfect lighting condition, scanning one component at a time, and you're moving forward. In this condition, yes, you can detect 0.1 mil or even smaller. I have hand scanner with this accuracy.
Perfect controlled conditions.
But go and use computer vision trying to scan 11 feet away from the framing table and scanning framing table that is 8 feet wide, 15 feet long. And give me the accuracy of 0.1 mil. It does not exist. We tried it over. We actually spent a year trying to utilize LiDAR, cameras, depth camera, and we end up with, I don't want to say complete failure, but it was a success that we learned what not to do.
Right.
So again, now we move to a different strategy. We are utilizing robots to support the computer vision. We have a master and I would call it, I don't like the word slave, but master and secondary robots that basically, main and secondary robot that basically help with the support. And this is our research that we spent 2 years plus on. Now we're confident in our ability to scan the components. We're moving from this to modifying the manufacturing strategies. Now, the other thing is wood is only our first step. I do have right now, if you look here, we bought CNC machine for plasma cutting, and we're moving toward LGS or light gauge steel within the next few months. So LGS has its own challenges. LGS is not as variable as construction wood, because these are manufactured components. You cut them as needed, and actually there are machines such as CAD frame that give you the stud based on the length needed for the wall. But at the same time, dealing with LGS in a robotic station has its own challenges.
And just to clarification, LGS would be the same idea of like framing construction with wood, but now with steel, right? Like you create like the structure of whatever building or house you want to create, but just with steel. Is that the
Absolutely.
idea? So like now you have like rods and bars of
Stud.
steel, exactly, studs,
Yeah.
and then you cut them to shape and then assemble them, put them together, and this is what you want to do with the robots.
Absolutely. So LGS is exactly what you said, because when you come to Florida, very few residential houses are made of wood, especially the older one. But because of the high moisture, even residential project, they don't want it to be made of wood. They want to made of steel or LGS, light gauge steel. And basically, as you said, you have top track, bottom track, you have the studs, C channel for the track, same, I would call it very similar framing procedure to wood frame. Now again, because of the assembly process of LGS, and that's something you may have seen it on my website, my professor, I would say over 7-8 years ago, he tried to create a new machine for LGS. And he'd done great work. We have a lot of research published, but it was still very challenging because we had to actually assemble the component manually, and the last step, which is the fastening, has to be done using the CNC machine. Now, we wanted to move from this to a completely automated LGS system, but the challenge we're facing is with the fastening system. What do you need to fasten those LGS? How do you ensure that the robot, when they're moving the stud, it's not twisted? How do you ensure that the C channel or C stud will be connected in the bottom or top track without any deviation? And after that, how do you ensure when you're actually using a bolt, using a rivet, using a weld, there is no deviation? So again, that's research that I have right now. A PhD student who's working on, the one who actually helped me assemble the CNC machine, and we have 2 more coming very soon. So again, when it comes to assembly-based manufacturing, we're trying to cover all of the point. Framing of wood was step number 1, and it has lots of challenges. Again, I don't know if you can see this. This is actually one of, and the reason I put it here, I called it pneumatic booster. I built this during COVID, because if you look here, when we build the end effector to accommodate for all of this component into the mechanical box inside, we were able to activate only 4 suction cup out of the 16. And only with 4 suction cup, we were able to carry over 100 pounds in suction ability to surfaces, such as gypsum board or OSB sheathing. Now, if we want to carry something heavier, I created something like this. You see this? This is nothing more than a booster. I can literally connect the airline here, have the input, link this directly to the suction cup, and I can activate 4 more. Okay. So now the 100 pound became 200. I get 1 more, it becomes 300. 1 more, it becomes 400. And again, at that point, we'll be limited not by the suction cup, but by the load capacity of the robot. Now again, the robot behind us are beefy enough, they're industrial, they can carry up to 150 kilograms, but this is in ideal condition within the load chart, closer to the center of gravity. The further you are from the center of gravity of axis 6, the more compromised in terms of load you have to be. So long story short, this here is nothing more than one of the many, many components that we had to build to support just the wood frame. Right now, we're in the process of building many more. We're even in the process of supporting human in the lead. Human in the lead, which is I would call it next generation of human-robot collaboration, where the robot becomes the tool and the human becomes the operator of this tool. We're developing haptic control system that enable human worker to actually move the robot wherever it needs to be done. So the reason I mentioned that, all of this hardware, software, AI, computer vision, robotic, so far it's only supporting wood, and we started supporting steel. Now, very soon, and we got blessed to have the fund for upgrade number 3, that is going to include mobile robot and cobots to enable our station to move from framing to MEPs and possibly finishes within the next 3 to 5 years.
What is MEP?
MEP, which is mechanical, electrical, plumbing. This is very common term in construction. So framing is only the structure. Framing is the bone of the house. After you have the bones, you need to have the wiring. You need to have the water line. My head's still here with the airline.
Right.
Water line, sewage line, ducting, and all
An
of this.
airline if you're doing like air conditioning or something like that, right?
It's ducting. We call it ducting,
Ducting.
but yeah, it's very similar. So we have all of these within the walls, within the floor system, and industrial robot will never ever be able to do that because they require dexterity beyond their
Right,
capability.
right.
And that's where again we're blessed. We have the fun to go to. I call the first version V 0.0, the one that we have in the pictures. Then I have V 1.0, the one we have the video. This here, you see the track is nothing more than V 2.0, and we're still in the assembly process. Again, if you come maybe a month or so from now, you're going to see completely different system. It will include 2 patented systems, my patent number 3 and 4, one for the robotic platform, which is going to utilize this track, and one for automated material supply. So all of these are still V 2.0. V 3.0, that we were planning to do it over the summer. If all goes well, we're still having difficulties communicating with the hardware. Again, hardware software issue, but it's going to include mobile robot, cobots to support these industrial robot. V 4.0, again, you see, again, we're lucky enough to have a good fund that support these 4 versions. We're going to move from penalized. Penalized mean 2D. You build wall panel, floor panel, with everything inside of them, but they're still 2D. Modular is volumetric, is 3D. To do volumetric, we need more dexterity. Now, the large industrial robotic arm can assemble walls, amazing. Once we incorporate the computer vision, we're going to address all of these quality issues, all of these material variation. Once we have V 3.0, we'll be able to go with MEBs, and V 3.0 will support assembly and additive manufacturing. Assembly in our station, which is part of DCB. Additive manufacturing is part of the largest 3D printer we have at UF in the engineer school, where the same, I would call it robotic system, can be mobilized between the 2 stations to explore different possibility of integrating those MEBs and finishes. Now, the 4.0, going back to it, is the volumetric, where we plan to utilize the new space. Now, again, one of the, when you're at the right place at the right time, I think that's what happened with us. The expansion in our DCB college included a new building called Collaboratory, and I was lucky enough and I would say blessed enough to be part of the space committee, and we assigned a robotic lab there with enough height to enable us to install gantry system. Because if you look here, we're in a good space, but the height is only 11 feet. If I include gantry system, it will be impossible to frame an 8-foot, possibly higher wall. It's impossible to assemble a modular unit that if you include the floor and ceiling, it could reach up to 11, 12 feet high. But with the new lab, we're hoping, because we have up to 15 foot high, we can actually produce modular unit completely ready. And this unit will accelerate the construction process significantly. And again, it will definitely improve the quality of the final product. And again, when it comes to human-robot collaboration, I'll leave that for later.
Right,
but yeah,
right.
This is always in our head.
Yeah, absolutely. Yeah, and it's super cool. Maybe we can touch a little bit on the more technical sides. So, talk to me a little bit more in detail of like the V 0.1 and 1.0 and 2.0s that you're working right now. For example, the hardware and software challenges that you have to overcome. You've talked a little bit about 2, for example, that if you want, we can talk a little bit more in detail of, like, for example, the scanning feature, like a scanning feature that you have to do to figure out the twisting or the deviations of some lumber. So how does that work? And that maybe might be a little more of the software. And talk to me about the hardware. Like, what does this thing do, and like how does it do it?
Yeah. So again, when we talk about the wood, this is for us the first, I would call it, system we're working on. And when it comes to the solution or challenges, they're part of the fundamental robotic research. So our computer vision challenge is part of the robotic perception. Robotic perception counts on the existing technology related to, as we mentioned, LiDAR, depth camera, 2D and 3D cameras. These are well designed for manufacturing environment, but not for construction. And I mentioned the example of in a factory, it's yes or no, easy decision. In a factory, I have the camera, few inches, 1 foot, 2 feet, very controlled lighting conditions. Here, and again, you may have seen like the LED light we bought here actually was one of the accessories we needed to run the experiment. So the fact that we are in this warehouse, even though we do have more or less constant lighting, but the changes in the skylight affected the accuracy of our computer vision. So all of these are part of the robotic perceptions. And as I mentioned, the first project we've done, which is developing a system that utilize a main and secondary robot working hand in hand with their own computer vision to estimate the 60 OF of different construction components, specifically wood stud. Now, after we did that, the next step, which is optimizing the sequence, optimizing the path planning of the robotic system to identify the required changes in the targets related to the assembly, nailing, pickup, and drop off. So manipulation is another issue, which is going to be an intersection between perception, computer vision, and robotic path planning. The other issue we're facing, which is material supply. Material supply is another main challenge because, again, when it comes to construction, every time you change the wall height, every time you change the window height, the location of the window, now we have different variation of piece of wood that need to be manufactured. Now, in manufacturing, they know we have piece 1 to piece N. We have different pallet, different racks. But the fact that in construction, this doesn't exist. Now, for wood, we developed in, I would call it V1.0. The reason I call it 1.0, it was part of patent number 2. We proposed a manual material supply that account for different construction variation, where we utilize Revit, which is a BIM software. BIM is building information modeling, which is 3D, I would call it 3D modeling of the building with different information related to construction component, material, process, and so on. So we took that BIM, and within Revit, we had a new app, a new add-on that create the shop drawing needed to manufacture the wall system. Now, once we have this in version 1.0, the reason I say 1.0, because we designed it, but before we actually start building the system, I invented version 2.0 that has the fully automated system. So in version 1.0, we had multiple levels. Each level has a maximum width to account for different variation. The shop drawing will generate all the detail for the studs, and we have an algorithm that utilize greedy algorithm to identify based on which level what would be the optimum number of piece of wood, what is the length that we can put under each of them. So a worker will get a sheet. This sheet will have a number of rows corresponding to the rows of the different material supply. On each row, they're going to have cells. Cells telling them, put 6 feet, 1 feet, 1.5 feet here. Mm-hmm. The second row, put 5, 3,
so
and 1.
The current inventory of the resources that you have available.
Of each building project. Because remember, when it comes to construction, each building is unique.
Right.
So every single time we have a new design from Revit, the step number 1, generate the shop drawing. Step number 2, create the material supply from the shop drawings. Utilize it to optimize the location of these material on the material supply that we invented, at least virtually at this point. And then the worker will know what are the pieces needed there, and the robot will know automatically that as well. Because for the person who's streamlining the design to manufacturing, they have to do nothing. They have just to select the BIM, identify the spacing between the studs, double checking that shop drawing are correct, click one button, it will export all of this information to RAS, generate the manufacturing strategies that we're going to export to our IRC or controller here. So that's all what the design manufacturing personnel will have to do. the transfer of information between the multi-level material supply that enable us to manage inventory in a more streamlined way, all of this will be done automatically. Now, for the human who's actually going and providing this material, they'll get, as I mentioned, a sheet, a printout of what piece of wood need to be done on which level. And again, these changes from one design to another, the greedy algorithm try to minimize the wasted space on each level, because let's say we're going in the design, we had 8 feet wide table, it could be 10, it could be 12. If I have 1 foot and I have 3 and I have, I don't know, like 5, these will not fit together. So I can say, let's go with 3 and 5 because this will optimize the level I have. Same thing, let's say I have 1, 2.5, 2, 6. When I say 2.5, it could be in fraction of an inches. I'm trying to simplify it, but we did a very quick estimate on a very simplified case study, and we had over 29 variation in the lengths of wood studs. When I say 29, that's literally 29 different pieces of wood that has to be cut. So we managed this in version 1.0 in our patent, and we were again blessed enough to receive the UF Invention Award for this because we tried to create a solution that doesn't exist today. Now again, the reason I call it 1.5, because it still requires a human to go cut the wood. Or we can have the robot or the cobot cut the piece of wood, then the human has to go pick it up and drop it off, or another cobot does that. Now in version 2.0, again, I've been talking a lot, I stopped know how to speak. Version 2.0 is the one that has the smart material supply, which eventually identify the sequence of the material and optimize it along the robotic platform. So the whole system will work together to identify the best sequence, best material supply. And again, even version 2.0, it's still an early version because we only introduced the hardware. We haven't controlled the system, how the robotic platform will communicate with the material supply. Can we have the material supply being proactive? Can we utilize online plus offline simulation? What if there is any issue during the assembly? How would we address that? So there is like a research idea that I'm working on, which is related to robotic fundamental, is how we can create a robust or robotic ecosystem where each and every piece, because the material supply could be considered a robot. It has intelligence, it has automation, same thing with the robotic platform, same thing with the 2 industrial robots, cobots, and so on. So how we can have a control system that manages this whole operation, I would call it seamlessly, and account for any unexpected challenges. Because while right now we're trying to focus on automation, we have another stream of research at the same time focusing on human-robot collaboration, or HRC. So let's assume when I have the material supply, we assign certain tasks to humans and certain tasks to robots. Now, we anticipate once our computer vision, perceptions is correct, our manipulation, our grasping, all of these are research that undergoing. These are controlled and they're great, but then the dynamic factor of human, the uncertainty of human behavior. We told the human, or the human knows what they need to do, but again, human error happen and mistakes happen. How will the system react to that? This is where I mentioned we're going to start introducing new fundamental knowledge related to robotics, new fundamental knowledge related to future of manufacturing. So these are the new area that we plan, and we do have different ideas how to proceed to address that. And the early version, as I mentioned, for human-robot collaboration is that new concept that we call human in the lead. Human in the lead is not like traditional human-robot collaboration. In traditional human-robot collaboration, the robot is absorbing the human and trying to assist in certain needs. So the robot is making decisions. And this is what we have, at least we're planning to do with the fundamental robotic or future manufacturing. But we want to create a new avenue, a new stream, where same way human can carry a circular saw, and a circular saw is a tool that replaces this manual saw, takes forever. They take it, they cut, they're good. A human should be able to operate this Same way they operate a circular saw, a nail gun, or any construction tool. And this is what we're trying to do. We're trying to limit the decision making to the human. So the robot will do what they do best. They'll do the dangerous task, physically demanding task, repetitive, tedious task. But then all of these variation that we're trying to address in stream 1 using computer vision, in stream 2, we don't want it at all. So let's assume there is variation in the dimension of the wood stud. With the human and the lead construction robot, we don't need computer vision at all. The human can go and, with the last step of the assembly, use their judgment, their skill, their dexterity to install it where it should be. Let's assume, as I mentioned, there is a human error. The human knocked the piece of wood off, pushed the whole frame. With the human and the lead, currently, we enable the human to correct these with the help of the robot. Again, I always like to try two streams. The other stream, as I mentioned, when it comes to fundamental robotic or future of manufacturing, can we have the robot help? We're not taking the decision away from the human, but can the robot help the human if mistakes happen? Can they even communicate? There is another research idea where the human and the robot actually teach each other. So I'm not only counting on the robot to make a decision, I'm actually counting on the robot to help the human improve their skills. So again, there is a lot of
How would that
areas.
look like?
It seems
Is it the robot identifying those mistakes and then trying to alert the human about them so that they can correct them or something like that?
so. Actually, this is still an idea we're working
Right.
on. The whole idea is we're going to create communication modalities. Communication modalities that help the robot understand what the human are doing, not helping them as what I'm doing now, helping understand the whole thing. And I don't want to reveal lots of information because this is research that I'm still working on. And the other type of modality where the system, not the robot is a tool, but the system, the AI, the centralized control system, communicate with the human the intention of the robot. So let's assume, and I'm just saying this for as an example, the human is expected to do their task, and their task include assembling component A. And let's assume the human didn't do it right or didn't do it on time. So there are ways we can help the human improve their skills. So the communication could be haptic, could be visual, could be audio. So the central system is observing everything, and they know what's happening, and they can become more or less like the informed foreman. You know, when you work on site and you have a guy who's like, yeah, you're doing great, but maybe do it this way, maybe do it this way. So now we're not only improving the skills of the robot, we're actually improving the skill of the human. So you don't need to spend years as a foreman, you don't need to spend years getting certificate. We're cutting the training time significantly. So someone with, I would say, basic knowledge of construction, once that system is developed, should be able to conduct tasks that today requires maybe 10 to 20 years of expertise. So again, there are so many things happening. There is the full automation, there is the semi-automation, which include human-robot collaboration, there is semi-automation that include human in the lead, and there is even the semi-automation that include both robots and human learning from each other. So this is from the human aspect. From the robot aspect, again, you've seen the hardware challenges, the perception, the manipulation. All of these are fundamental robotic issue that we're trying to address. And again, it's not the same. This is the message that took me 3 years moving between manufacturing and construction to tell them it's not the same. Robot cannot solve construction issues with its version today, but robot has the potential to be a key driver for productivity improvement, safety improvement, and quality improvement. It's not ready. We still need to do all of this system development, control system, hardware, software, but on the side of the construction expert, we can do it. There are people who think it's too easy and people think it's impossible, and we are bridging the gap between the two by saying
Actually doing it, which is the thing where you actually learn what are how easy it is, right?
it's not how easy,
Or like
how doable.
and how difficult it is, right? Like you actually understand, oh, this turned out to be sort of easy, but this turned out to be like nearly impossible, right?
Again, I always tell people that if it was easy, they would have done it a long time ago. We plan to have a robotic station that costs 500 more or less $1,000. So if developing a multifunction robotic station that conduct construction tasks can be done easily, it would have been done years and years ago, because when we did the return on investment, or ROI, based on our current cost, which is more or less $500,000, it was less than 6 months. So a factory, a small factory that produce less than 85 houses, they can get their money back, saving from labor cost, literally within 6 months, 60 houses more or less. So my point is, if it was easy,
They would have done it.
it would have been done years and years ago. So it's not easy, but at the same time, it's not impossible. Because again, there are people think easy manufacturing side, and I tell them do it. Like anyone who tells me it's easy, even people, they argue that Ross exists and Ross can model everything. I'm like, have you worked with Ross? Do you know the challenges of programming? What kind of issue you have every time you try to automate a path planning? What kind of singularity issue you're facing? So just because technology is there, whether
Yeah.
hardware, it doesn't mean it's ready.
Yeah, we can talk a little bit on that, because I've also had this sort of frustration, as you mentioned, that in the robotics research side of academia, it seems that a lot of stuff has been happening and like a lot of improvements in research and new models come, but then it's kind of hard to get them to the actual industry, to like a company that makes money. So it seems that still the research to application gap is still sort of large. So how are you trying to bridge that gap? Like what specific challenges have you encountered, and how have you solved them? Like basically what I'm asking is how do you turn something that is working now in the lab to something that then a company can use? And maybe you can touch a little bit on the efforts that you're doing with, for example, the UF Innovate, of, in my mind, that is the thing, like the organization that bridges that gap, right? It's like, you are doing cool research, let me fund you. I don't even know the specifics, but let me give you some money, or at least let me award you of the efforts that you're doing, so that this actually ends up in a company, for example.
I again, this is one of our daily struggle, because as a research institute, we're expected to generate knowledge,
Right.
which is very fundamental, and I do respect that immensely. This is one of the reasons I switched from industry to academia. I don't know if you checked on my CV. I worked over 10 years in construction as a project manager, as director of R&D. And when I say director of R&D, research in industry is not like research construction. Research in industry is applied, very applied. We need something, we develop a solution. Research in construction, when it comes to academia, it's too high level. And again, I completely understand that, and this is where we're trying to open a new avenue. So all of this idea, what I mentioned about robotic fundamental, perception, manipulation, future of work, human in the lead, human robotic, all of these are fundamental issues that we're trying to address. But at the same time, because I came from industry, I have a soft spot for implementation. I heard from many people here in academia where they say research should stop where development starts. They hear R&D as two different letters. They say we do the R, someone else has to do the D. I don't like that. If it was the case, it should be R, then something D. It's called R&D for a reason. So we need to develop a solution for our research. We need to create a technology that is almost ready to be deployed. Now, there are few faculties that focus on this issue, and I think myself lucky enough to have worked. If I didn't have those 10 plus years experience in construction, I may be only focusing on research. But due to me working in the industry and seeing the need, understanding that there is a great research idea that never see the light of the sun. They get developed, then no one, as I mentioned, maybe it's a great idea to solve a fundamental issue in construction, but the researcher never actually developed a system that can be deployed. No one took the effort to put that system in operation, then it died. They publish paper, great, but there is nothing on it. This is where I wanted patent. And again, so far I've been here for a few years. We have 4 patents for a reason, and that's where UF Innovate role plays a key component. We're trying to develop the technology that's ready for implementation. Now, whether V1.0 or very soon V2.0, we are at TRL 7 close to 8. The reason I say 7 to 8 because in TRL they start with 0 to 9.
What is that? I'm sorry.
Technology readiness level.
Okay.
Technology readiness level. We're almost at 7, and we're hoping to achieve.
Is that
8.
up to 10?
It's up to 9. So 9 means it's ready. It's already verified. They tested. It's good to go. You're good. Now the reason I say we're at 7 because we have the prototype. We haven't done the rigorous testing yet. You have to do testing. You have to do like in the field testing and so on and so forth. Again, when you reach TRL 7, and we're hoping within the next year or 2 to reach 8 or 9, our technology is built for a factory. It's not built for research. I'll give you an example. I had people from mechanical engineering and even students. They came to the lab and they saw this and they're like, when we were students, we used to use ties and duct tape. This is literally how to have a prototype. Now there is 3D printing, things are different. When they look at, if you look even at this one here, all of these components are industrial components. Nothing of this. Again, they might not be the highest end. We use prototype and eventually we can go with higher end. But all of these are things you can see in an actual factory. If you look at the design of our end effector, this is a design that is like that's meant to be deployed in a factory. So again, this deployment takes time. This deployment take effort. This deployment costs money.
Right.
And again,
how does that work, right? Like, again, how does the patent get it closer to like some sort of, is the idea that then the patent would be used by some sort of company, maybe started by you or something like that?
So again, there are few faculty who done great work moving from a patent to a company, and we're hoping to be one of them.
Right.
And I know UF Innovate are encouraging me to do that as soon as possible, but I like to do things right. I like to have all the component ready and then produce the, I would call it end result that is ready for deployment. So we're one milestone away from actual deployment. So once we achieve this milestone, and we're hoping to have it within the next 6 months or so, again, life happens, it might take a year or 2. Once we have this milestone ready, now we may be able to reach TRL 8 and possibly even 9 once we have it deployed in a factory. So this will be a startup, whether the technology could be adopted by an existing company. The business model is something we're still evaluating how to proceed, but this is one of the things that we use to bridge the gap between research and real life. And again, the way I see it, the time that we spend, even though some academic might think that it's waste, because like I shouldn't do that, but do you see here? This is literally a scratch. I was building the airlines and I was wearing the safety, everything is correct. One of the screw flew away and hit me. So we literally have blood, sweat, but so far no tears, so we're good with that. My whole point is there are people who see this as a waste of time. There are people who think I can hire someone to do the work. And in reality, we can't, because we're building the prototype as we create the research. This is a living system. So when I said we literally came up with the idea to connect 2 airlines together and have different systems, one for the robot, one for the CNC machine. I thought of the idea, I'm like, let's do it. Now, instead of me spending a week redirecting all the line, creating new system, developing all of that, I could have developed more fundamental research. So the whole idea is I see the value in development. The R is very important. And of course, we have to do it. As a research institute, we have to publish, we have to submit grant. This is fundamental, and I'm following that. But I don't see the D as a waste of time.
You're hoping to do both, right?
We
hoping to do both. Good.
Absolutely. And this is, again, when I said time and effort, another component, very big component, which is money. Like these equipment here, they cost good money. And we are lucky enough to have support. So again, when we said we got blessed by getting fund for industrial construction engineering, because I was blessed enough to be part of the team who discussed the idea and I was part of the team who led the effort, I was very vocal about the need and everyone was very understanding. So that's where we have the budget to go from 1.0 to the version right now we're working on 2 to 3 to 4. So a combination between time, effort, and money is essential to move from research to development. And again, I don't see it as a waste of time because I know lots of people, they said, you should publish more paper, you should do that. No. I want to have a system that the company can use hopefully next year or so.
What are recent developments in the foundational robotics research that has accelerated development in the specific applications that you're trying to solve?
Now, when it comes to fundamental robotic research, again, the good news and the bad news is they're doing great. So the good news is they're refining metrics, improving the load capacity, improving the speed, but they're mainly for different robots. So if you look at the latest research, again, I'm not the expert in fundamental robotics, so I'm going to speak based on my current knowledge. So I realized that most of the research in robotic arms is being done by the companies themselves, like ABB, KUKA, those companies. They are invested in improving their performance. But when I look online and I see fundamental robotic in other aspect and research, they're going with the swarm robotic, drones, mobile robots, humanoids, all of these. So there is good research, perception, manipulation, all of this. But I wouldn't say it's very helpful for our application. The reason for that, again, you need someone who understands there is a link between the two. You need someone who understands that when it comes to construction, it's not the same as manufacturing. I would anticipate, again, this is nothing more than prediction. The reason there is not much research fundamental for industrial robotic arm, because people in manufacturing, they think we're there. Remember, that's the thing that we discussed for like the first few minutes, where I said they assume these industrial robotic arm can be deployed in construction. So their assumption that it's ready may be the reason they haven't invested time or effort to make it suitable for construction. Now, for us, the fundamental robotic research we're doing is related to manipulation, is related to perception. So we're not actually redesigning the robotic arm itself. It's the end effector, the computer vision, the control system. We can even include the haptic control system and so on and so forth. So we're lucky enough to be in a situation where we are leading the effort in construction robotic for assembly of larger component. When it comes to construction robotic, mainly right now, they're like mobile robot. They have the four-legged, like, this few case study you've seen. They're cute, they're nice.
Like
but
a spot robot from those
Spot.
Boston Dynamics.
I'm trying not to mention the name, but like Spot, I've seen it used for scanning site, inspection, and so they're great. But I'm thinking a bit more.
Right.
I'm thinking about changing the industry. And
Have you toyed with the idea, for example, you mentioned the humanoid. I haven't really thought about that because right now there's a big investment in humanoids. And they potentially could be like one of the form factors of robotics that are adaptable, as you mentioned, that maybe it doesn't really make sense to have a humanoid in a factory setting doing manufacturing, but maybe in construction, right? They can do like the actual physical stuff. I don't know. I just thought about that.
No, that's a good point. The only thing, and I know people might feel it sound really like, why you're saying this. I don't want people to lose their jobs. Someone who's doing research on robotic and cares so much about human jobs, this could be something new. If we're going to invest in a humanoid, then what are workers going to do? Remember, one of my research is human in the lead construction robotic. Even when I talk about human-robot collaboration, I'm trying to improve the skill of a human worker. So I'm not saying robotic shouldn't be used or AI is the enemy. No, of course, we have to use it. We have a saying, when ChatGPT or any of those AI platforms came to universities, there are a lot of professors who were nervous. Like, what are we going to do? How are we going to manage it? And I remember one of the senior professors, without mentioning name, he mentioned something very nice. He's like, we were panicked the exact same thing when Google got established, that student can be able to search anything and they're going to download all the articles. So the technology is not the enemy, it's how you use this technology. And I don't believe a humanoid is the good place to invest. Invest in robots like these that help alleviate physical work, help improve the quality of life for worker, but why to invest in a machine that replicates a human? We have enough humans, so don't worry about it. And if we're worried about productivity, labor shortage, we can make the machine more efficient.
Right.
Same way I mentioned.
So maybe like an argument of like it's just too much effort to do something that you can already do pretty good.
It's not too
right?
much effort.
Like
They're
too
going to
much
be
effort
there.
and investment, right?
Again, I think maybe not today, but if they continue this path, 5 years, 10 years, I'm not prophet, I have no idea. But they're going to reach a point where humanoid, if they continue this path, are as dexterous as human. And there is an argument that AI could become more intelligent than human, and I believe that because we have a limitation on how much information we can process versus a machine. I just add more RAMs, more processors, more memory card, etc., and I can do whatever I want. So the whole idea is we want to support the human, not to replace them. So I don't want to say I'm against, but I don't believe humanoid is what should be pushed forward. We should see robots as cars, as a machine to improve our life, not to replace us. So as I mentioned, when I said automated, semi-automated, same way we have manual car and we have automatic car, we can have fully automated robotic system and semi-automated. So let's assume I need to build a community in a week or so, and the speed outweighs the human-robot collaboration, then I drop fully automated robotic system to build this community within a week or so. Let's assume, aside from this, when it comes to affordability, for job creation, for Made in America, all of these, I need to ensure that humans have good income. We all know that in bad economies, the government usually spend on infrastructure to create jobs. So I'm trying to create job, not to replace job. So my point is, instead, as I mentioned, I go back to my example. In the old days, someone has this old saw and going and cutting piece of wood. Now they have circular saw, meter saw, whatever it is, in seconds. That's how I see robotics. Now, do they need to use computer vision, AI? In certain research, maybe, and that's where we have perception manipulation. In others, I told you, in the human in the lead, we said, nope, we need to minimize AI. AI should be only related to the coordination of the robot, and every decision making has to be done in the hands of the human. You see? So that's where it's a thin line. But again, I don't like to say I'm against, but I'm not with humanoid. I don't like this idea.
Maybe let's finish on the human collaborator side. Like, what specific research progress or like what plans are you trying to make in there? For example, saw a journal paper I thought it was cool of you trying to estimate the safe zones of where humans can operate near robots and build some sort of predictive model of how that interaction happens. So yeah, can you touch a little bit on that? Like how exactly and specifically what are these research areas that you're trying to explore in that human-robot collaboration?
Now, when it comes to construction, one of the key differences between construction and manufacturing is, as we mentioned, design changes, customization, material variation. And another thing is human-centric, because there is a lot of component that always changing, and you have a lot of people working around. And today, if you go to any manufacturing factories, you're going to see a fence around industrial robot.
Right.
You're not allowed to work in the vicinity of a robotic arm, because
this is too dangerous, right? Like this thing
can
break your entire
then
bone.
create a serious injury.
Right.
Let's keep it like that.
Right.
So how are we going to solve this issue? If I'm going to have worker working next to robots safely, I need to understand a few things. I need to understand the ability of the system to perceive the human. I need to understand the layout of this factory. So if I'm going to have a robotic station in a factory, how big, how small? These are the questions we try to answer in the first research, where we said, okay, let's assume, and by the way, we haven't done real life human collaboration because it's still too dangerous. We used mixed reality experiment because we're still trying to test. Again, computer vision is one of those things that we're still
Right, specifically
evaluating.
if you want to see like, oh, when are the accidents happening, right? Like maybe it's not
Exactly.
the best idea to do it.
And
in real
by the way,
life.
in the experiment, you may have I don't know, like the results were encouraging. So most of the incidents were not the human hitting the robot or the robot hitting the human, because we control the speed of the robot. We didn't go like, when you have a car, you have 200 miles per hour and 10 miles per hour. So we were like 50, 60 miles. So the robot is moving, but it's not like, as in the human cannot avoid it. So even in the MR experiment, there was no incident between the human and the robot. The most incident was with the material. The human is moving a piece of wood. They may have hit the virtual robot, not the real robot. Same thing with the safety envelope, because we created safety envelope around the human and around the robot, and we utilized different distances as the personal distance, as in the distance around each joint, each link, and so on and so forth. So the majority of the incidents were between those envelopes or between the material. But at the same time, again, for us to have this in a factory, we need to ensure it is 1,000,000% safe. And the first research, as I said, to evaluate where would be the best location for a human to move around the robot. Now, this by itself is human-robot collaboration, because when it comes to human-robot collaboration, there are different modules. There is a module where the human and the robot doing their own things, or they're collaborating, or again. So we assume that the robot is doing a task and the human is doing another task, but they're in the same location. They're collaborating basically. And again, I have very bad memory. I forgot the 3 names of HRC. I'm always like that. There is 3 modules. Anyway, so the first one where the robot is doing their task and the human they're doing theirs, and the human is working around. So how large or how small this station need to be? Because when we're asking construction company to adapt robotic, one of the questions I was asked, so what is the space you need? There is a new factory, but the majority of the factories are old. So there is legacy versus state of the art. If you build a factory state of the art, I can have the station as big as I want. If I focus on legacy factories, the one that already exists, and they're thinking of adapting robotic, $500,000 is not a big investment if, and finger crossed very soon, we prove it works. As I said, ROI 6 months, this is as aggressive as it can get. So let's assume a factory is invested and want to spend $500,000 on improving their factory, but their factory is limited in space. They can only afford, 30 feet by 40 feet. So how would we ensure that if there is task where the human has to do their own and the robot has to do their own, we can still have safe collaboration between the two without having this huge fence that prevent collaboration altogether? So that's the first experiment. Now, the one that we're working on right now, as I mentioned, which is human in the lead. And actually, we have a paper got accepted. Literally, it's in publication, which define out of all of the tasks that the robot can do, which one requires human guidance. So when it comes to construction, as I mentioned, between design changes, between material variability, if I don't want to overuse AI and computer vision, if you do it, then we are at the point where we may lose human job. That's the first risk. The second risk is, what if AI fails? And we've seen it happening. And I anticipate this keep happening for years to come. So to avoid all of this issue, we said there are automated tasks. They are repetitive. You do the exact same thing over and over, no matter what's the design. There are guided tasks where you have to have human guidance to do the last step, finalize it. And there are manual tasks. There are tasks that it doesn't fit these type of robots. It may fit the next generation that we have to 3.0, which include the cobots, but they're impossibly done here. So we classify the construction task into those 3 categories. And right now, actually, the student that is working here right now, he's developing the manufacturing procedure to enable the robot to conduct these tasks, the automated one. And we have a team with the ECE, Electrical and Computer Engineering, helping us, working with us on this proposal to develop the haptic control system that include touchscreen control with all of this information to support the collaboration between human and robot. And with the human and the lead, the robot is no longer a collaborator. The robot is just a tool. Now, again, automated, semi-automated with a human and the lead, this is where we're at. It is semi-automated, but this station is nothing more than a nail gun.
Yeah, maybe what are the types of tasks that you envision the robots collaborating and the human leading the robot into actually accomplishing this task more efficiently, cheaper, whatever.
So what happened is, based on our analysis, we've done product analysis, design analysis, tolerance analysis. We determined that there are tasks, and most of them related to the component that has multiple sub-assemblies. So let's assume you have an opening. The opening has multiple components between header, cell, king, jack, scribbles, and so on and so forth. So the acceptable tolerance in construction material might compound and result in unacceptable assembly. So wherever we require computer vision or AI to account for all of this variation, and this is something actually we're working on as well, we wanted a human in the lead to take the robot out. You are a robot, you're nothing more than a tool to help me do my job. So you help me do my job, you go bring the material, from the material supply, bring it to me, and I, as the human, as the carpenter, as the tradesman, I'm going to use my judgment, my skill, my dexterity to determine this piece of wood that's slightly bent, slightly twisted, how do I place it in the right location so that the final assembly is correct. This is what they do today in real life. In real life, when I said you buy a piece of wood from Home Depot or Lowe's, and it's almost impossible to get two pieces exactly the same.
You mentioned that, yeah.
Framers do that today. They literally use their judgment call, their skill. This is bent to the left, I'm going to twist it to the left, this is to the right. They have their own common sense to deal with that. So
that would be difficult to automate in the
it's
near future,
semi-impossible.
right?
Now, semi-impossible, the reason I say semi, because in our current research, we're trying to control it to a degree. We're trying to, after we scan the piece of wood defined with 60OF, right now we're working on a system that determine an acceptable range of tolerances. So for instance, if you go to framing, sometime framers, they'll frame anything. Like even if the piece of wood twisted beyond repair, they'll still use it. With a human in the lead, we can do that. There is almost zero material waste. But with a human in the lead, if anything beyond the acceptable tolerance, sorry, not the human in the lead, and the automated one, anything beyond the acceptable tolerances, we might say don't use it. Because in construction, piece of wood should not exceed 1/8 of an inch. If it's half an inch tolerance, 1 inch, then just throw it away. So again, this is the fine line we're trying to walk, and with the human in the lead, the good news is we're building human skills. We are creating a new career where, again, this guy who's cutting a piece of wood day in and day out, possibly because of ergonomic issues, they're bending up and down. When you have on site, you cannot control how you assemble. So all of this ergonomic analysis, safety analysis, haptic control system are included in our station to improve the life quality, improve the skills, improve the work condition of these construction workers. And again, for today, anything that requires decision making. So let me ask you the question: can a nail gun decide where to put the nail? If you tell the nail gun, you're gonna nail in this position, yeah, I can put it on a compressor and again turn back and forth, repetitive motion. But if the nail gun has to determine, and by nail gun I could say robotic arm, this piece of stud is half an inch twisted, or there is variation of half an inch. I should go left, should I go right, should I twist it? Now all of this decision making is in the hand of a human worker, and this create, we're hoping, self-satisfaction. Because we all feel good. Like when I develop a software or I work on an end effector or even I cut myself, but when I finished, I'm like, I connected two systems to the same air compression. I'm happy. And like industrial system, not small one. So this self-satisfaction is part of the equation as well. And this will drive skills, will drive the next generation to choose a career in construction as well. So
yeah, maybe let's wrap up on that note. Whether the people that are starting to choose these types of careers and go into these types of applying this what looks like a futurist technology to like real world applications, what are advice that you have for those types of people that are trying to do this thing?
my advice is don't have your head in the past. Look at the future. just because construction today might seem physically demanding, might seem dangerous, remember there are people like me and many, many more in UF and many other universities who are trying to make your life better. So keep an eye on us. Make sure when you make a decision related to your next career is understand that the future is bright. It's going to be much better. I'm not trying to sell construction, but yes, the future of construction will be much better than the past because we're at the right time. We've seen this AI movement, we've seen technology improvement, we've seen robotic advancement. We are literally at the intersection of revolution. I always like to use this terminology because maybe it doesn't sound much, but 5 years from now, I anticipate things to be significantly different than 5 years ago. So again, my advice is keep your eye on the latest research because you may like what you see.
And there's optimism to be had, yeah.
Absolutely.
Thank you so much.
Thank you so much.
Yeah.
Pleasure meeting you, sir. I know it sounds contradicting when we say reduce labor costs but create job. But the answer is go back 50 years, 100 years ago, where they moved from horses and car to cars. I actually had this discussion with one of our admin in the university, and I'm like, we're not trying to reduce jobs, we're trying to upgrade jobs. And he's like, I agree.